Hello, we are team number 3, Rocket and Capsule Communication System. Our group members are Valeria Mendoza, Jose Rivera, Montserrat Salas Nava, Neil Smith, Raphael Velázquez, and myself, Cesar Franco. The topic is Systems, VVT Methods, and is related to testing. We will be addressing 6 testing methods available in chapter number 5 of the book Verification, Validation, and Testing of Engineered Systems by AVNER ENGEL, pages from 378 to 436. In specific, this is the content that we will be reviewing through the presentation. We will try to relate the topics based on the projects of the class. That's why we decided to include a little bit of background. Then we will be reviewing the section 5.4, Black Box High Volume Testing. In this section, we will be addressing the performance testing, recovery testing, and stress testing. For the section 5.5, Black Box Special Testing, the subject will be security vulnerability testing. And for last section 5.6, Black Box Environmental Testing, we will be reviewing destructive testing and reactive testing. Background. The project for group number 1 is to create a smart manufacturing lab on the second floor of the UTEP engineering building. They are trying to implement augmented reality, additive manufacturing, and autonomous robots. The project for group number 2 is an autonomous mass transportation system for UTEP students. They are proposing an autonomous vehicle capable of supporting 15 to 20 passengers that will follow designated routes selected by the bus itself. The system is trying to minimize the time wasted on current bus stops. The project of my group number 3, we will develop a relaunchable vehicle and rocket that will provide a whole new experience for human travels. The goal is to make space travels more accessible to the public. The project of group number 4, they will implement augmented reality to the train manufacturing industry in order to train the staff and improve the pre-cut process done on materials as a sewing reference to virtual reference. Hello, my name is Cesar Franco and I will be addressing the performance testing section. Testing. The purpose of performance testing is to demonstrate that a system meets its defined set of performance requirements. 3 good examples can be verify early operating faults at full load, establish a baseline for future regression testing, and discovery of bottlenecks. As we can see on figure number 1, here we are representing the autonomous bus of team number 2. The system is fully loaded. There are 2 buses trying to use the same road to get to the final destination. Using performance testing, we will be able to avoid this type of bottlenecks and come with a solution on early stages of the development. The performance testing entails a carefully controlled process of measurement and analysis of the behavior of a system that is being tested. As we can see on figure number 2, there are 2 buses using predetermined paths, and we are measuring the number of buses, the speed, the number of passengers in order to test the performance of the system. As we mentioned before, performance testing is to evaluate whether a system can operate at full performance loading within its normal intended operational environment. In non-technical words, it questions if the system is capable enough to make customers happy. Reliability. A performance testing should be performed before a system completes its development period so as to verify whether if the system meets specification and is reliable enough to go into production. If the system exhibits performance degradation, a performance testing should be repeated to ascertain the cause of this setback. 3 main concepts to take in mind for performance testing. It assures performance, locates potential problems before customer, and tests functionality under real-world conditions. Functional testing deals with the risk that the system does not function properly, whereas performance testing deals with the risk that the system will not perform enough. Ignoring performance risk yields usable systems that may be slow, systems that may be functionally perfect but unusable, or systems that are unreliable. As we can see on figure number 3, it's a diagram of the augmented reality glasses for the train manufacturing industry. We can see that the use of only one processor instead of two, as figure number 4, it will lead us to a functional system but a very slow process. Method. There are existing methodologies used to plan the performance testing. There is a document called PTP, Performance Test Plan. This document should cover information related to the entire process of performance testing, such as system performance requirements, funding, manpower, schedule, materials, infrastructure, target system, and testing setup. The tester must verify whether each system parameter meets its required performance envelope under a required system load. Performance testing usually includes load and volume testing, that is being tested to demonstrate the system's ability to deal with the required inputs and outputs. On figure number 5, we can review a performance testing environment setup for the augmented reality glasses. There is an environment simulator and performance simulator to record and the system. We have two different inputs. Number 1 is a 3x3 matrix in order to check the system, and then a second input of 20x20. This is with the intention to overload the system to measure the performance. Typically questions to test performance. In this slide, we will work with the rocket example of team number 3. Figure number 6 shows an explored view of our rocket systems. On figure number 7, we are zooming in the rocket engine system in order to relate with our questions. Question number 1, response time. How long does it take to complete a task? As example, we can refer to the time of the engine to start. Question number 2, external capacity. How many external systems or users can the system handle? As example, we have the number of pilots in the rocket. Question number 3, resources. How many resources are utilized by the system? One good example is the fuel to power the engine or the materials used in order to build the rocket. Question number 4, reliability. How stable is the system under maximum required overload? Here we can refer to the temperature resistance of the materials at full speed. Performance test procedure. A typical procedure for conducting a performance test usually covers the 9 following steps. Step number 1. Gather and document the performance requirements. Step number 2. Develop a PTP plan considering the parameters that are being tested. Step number 3. Select and purchase performance test equipment. This will imply to train staff. Step number 4. Develop test scenarios. Step number 5. Develop the performance testing environment setup and integrate with the systems being tested. Step number 6. Execute the performance test scenarios. In this stage, we will increase the load gradually. Step number 7. Collect test results, statistics, and graph in order to analyze the data. Here we have to decide whether if the system meets their performance or not. Step number 8. If system does not meet specifications, the system engineers needs to solve this issue by replacing hardware or software elements of the system. Step number 9 and final, generate a performance test report. Here we have to state if the system meets its performance requirements.
Hello all, my name is Neil and I'll be going to the recovery testing verification method. So what is recovery? Recovery is a function of a system to not cease operating or completely crash when there is a fault in the system or a fault in the system process. Recovery is not only to not cease operating, but it's also to regain back to its system performance before the fault. and it also goes back to performance without any loss. The most common example is in computer software. I think it's happened to everyone that working on a document in Microsoft Word, the computer crashes. And this is part of the recovery process. It realizes it crashes, it shows some sort of screen, and it restarts back to normal. And then what you were working on, it's either completely saved when you go back to it, or most of it is saved before the crash. This is a recovery function of the computer, and this process must be verified, and it's verified through this recovery test. Faults don't just have to be software related, it can be related to multiple aspects of the system. It can be a hardware fault, such as missing a wire or missing a circuit board, or perhaps one connection is not available. It can also be human error. An example of a human error fault from the augmented reality project is that a person might accidentally cover the camera, and if it covers the camera, they won't, show that data. So how will it recalibrate once that fault is removed and recover back to its normal function? So, how exactly does the recovery test play out? Since recovery starts from a fault in the system, the first part is to verify the recovery function is to inject faults into the system. So you build a system, now you have to find ways to break it down so it can recover. With respect to the RE-Lander project, one subsystem for recovery testing is the navigation system. To inject faults into the navigation system would inject faults into software processing the navigation system goes through. This can be done with a software mutation program. What this program does, it messes with the code. It messes with the ones and zeros in a random order so that it messes with the system process. It doesn't compile correctly. The next step of the verification method is to then observe the system recovery process. The recovery process usually has a couple steps if the system does it automatically. It will go through detection of the failure, reinitialization of the system, and data recovery. Recovery testing is most important on systems and subsystems that work in real time. Again, this includes computer programs which work in real time when we're using them. It's also critical for safety critical systems. An example of a safety critical system is the RE-Lander life support system. The oxygen tanks are safety critical and any fault would need a recovery process, and that recovery process would need to be verified. Other subsystems is the driver assist subsystems, which also work in real time. This includes the UTEP automatic bus navigation system, as well as the RE-Lander navigation system. These would be considered driver assist programs. And another type of subsystem, which also needs recovery testing, is transactional systems. Data loss can mean many resources are lost. It can mean whether money was sent or not sent. So recovering before the fault occurred is very important to make sure that no money is sent to the wrong person or the correct amount is sent. And finally, we have a recovery test example. So this example, I took the liberty using the UTEP automatic bus. So step one would be to induce a fault in the system. The fault here is that the tire is not in use. Either it's removed or it's punctured in some way. And if it's automatic, the fault would be recognized. And then step two, we would observe the recovery process. Here, since it's mostly hardware and it can't really fix itself, it would send out a maintenance report, and then once it would put itself in standby. Then it would be recovered and repaired. And then step three is that it would goes back to its normal functions without any loss, and that the data stored in the error logs is complete, it's correct, and it can be that integrates back with other parts of the system, such as some type of device to get the diagnostic reports.
Hello, my name is Ray Velasquez, and today I'll be discussing stress testing in section 5.44. The purpose of stress testing. Today we'll be focusing on three areas, which will be the launch, space, and the re-entry environment, which would be to determine the effectiveness and the behavior of the spacecraft system, which will be in focusing the act of the optimization and the temperature of the pressure conditions and determining the maximum stress load of the strength load of the spacecraft system, which it can withstand under the action of the stress of sufficient magnitude of the small cracking that it will initiate at the points of the stress concentration. Once the cracking is initiated, and it will intend to grow in the three directions, which would be in the X, Y, and Z axis of direction of the tensile load. Finally, the material in having the reduced cross-sectional area is experienced in the fractional direction. Perhaps the fatigue is the most important fatigue nodes conditioning area of the mechanical design. So the focus is to provide the engineering team and to develop the testing for the spaceflight vehicle in the human flight areas. And that will be in focusing in the human flight vehicle system, the integrated environmental testing, and also the flight design. Stress testing plan. So the team was able to come up in three major areas, which are human flight vehicle system, integrated environmental testing, and lastly, flight design. So in these three main areas, we're only going to focus on space flight communication, launch environmental, and also guided navigation and control. So the idea was to come up with a test that will define the ability of the stress test assessment, which the spacecraft can currently sustain in an active operational status. So there's a conditionable variable that will observe in the following discussion, that it will assume that the fatigue strength can be characterized in a strength by a single SN curve to ignore the moment on how the large scale in the data can be managed. Communication. So within the communication of the spacecraft, what was taken into focus in the interface, which would be the design and the performance of the antenna. So taking into account the antenna was analyzed in a 3D frequency electromagnetic analysis to verify the microwaves and the antenna measurement. This was taken into account of a test and capability of the antenna radio frequency design. By doing this, we were able to assume that the material will be remain in an elastic state. The stress at this point of the stress concentration is computed and compared in a radio frequency in an SN curve. Now, the local stress and strain are estimated at a point where the fraction of the antenna in a fatigue cracking must most likely occur and is assumed at the local yielding will continue at a point at the effective local yielding is included. Now, taking this into account at a delta K, it was equal to a Y and is applied at a range where the cracking depth for a surface will yield at a width for a penetration flaw, and the geometry is at a correction factor at which may depend on a factor of a variable A. The specifications. Now, taking into account of the parameters and the values, we were able to conclude that the measurement for a far field antenna radiation distribution pattern in a condition to the horn shape at 150 feet long at a cross section 40 by 40 feet, and also approximately 115 feet at the tip, in addition to a position at a dual and also at a single position handle at 600 pounds. Also taking in account to the structural and materials, we also were able to account in for the parameters and the values of the load capacity and the stroke range. So 220 pound-foot up to 150 pound-foot and 6 inches to 57 inches, and a temperature range negative 300 to 800 degrees Fahrenheit.
Hello, my name is Jose Rivera, and I'll be talking about security vulnerability testing from section 5.5.2. What are security vulnerabilities? A vulnerability is a flaw that is exposed by a threat or actor. Security vulnerabilities are unauthorized access to a system for the purposes of corrupting information, financial fraud, stealing data, or causing a system to crash. Some attacks may be carried out in the form of malware infection, which can range from high to low impact. Examples of this are viruses, which are human replicated programs, worms, which self-replicated across the internet for a brief period of time, Trojan horses, which are seemingly innocent programs with malicious code, backdoor, which creates an access channel for an actor, mobile code, which is malicious programs obtained or installed by the user, sticky software, which prevents the user from uninstalling the program, and cryptographic work, which is encrypting the user's data, making it useless, adware, which are pop-ups, and the phishing attacks, which are email communications requesting personal or company information. A little bit of background. These threats to computer and networking systems are changing and expanding rapidly. Studies have shown that malware attacks have increased exponentially since 1991, as suggested by the F-Secure Corporation from Finland. More systems support web applications, which are the primary targets. Hacking tools continue to improve. Amateur attackers are becoming organized, and complexity of malware programs continue to increase dramatically. And the graph there below shows the exponential growth from 1991 to 2007, with reports of up to 500,000 malware attacks. Security vulnerability testing. A secured system must prevent both external and internal attacks. Testing can occur during the different phases of the lifecycle. A System Security Test Plan, SSTP, identifies the requirements that will be placed on the system along with the security architecture. The SSTP would also identify the types of testing to be conducted, which are explained below. System tests, these tests verify the fulfillment of the requirements. Operational tests demonstrate the system is operational ready. Vulnerability tests identifies the current vulnerabilities by scanning methods, which are port scans, password checks, or system patches, and penetration tests, which evaluate the system by directly attacking the system in efforts to attempt to gain unauthorized access. This requires coordination and formal authorization. Now, the testing process. The SSTP is utilized to develop, implement, and manage the testing process. An example of a laid out testing process from the National Institute of Standards and Technology is explained below. Phase 1, scopes and rules of engagement, which identifies the elements to be tested as a scope and also identifies the rules of engagement. Phase 2, develop evaluation methods, which are the test procedures and methods to be created with the information to be reported. Phase 3, security testing execution. The actual testing of the hardware and software occurs and the reports are documented. Phase 4, perform corrective measures, which is the phase in which corrective actions are taken to mitigate or eliminate the vulnerabilities. And Phase 5, retesting. This phase identifies the vulnerabilities that have been addressed as well as no new weaknesses to be inadvertently injected during Phase 4. The testing team responsibilities. They identify the assets, which is the data or the systems that provide crucial purposes requiring a secure architecture. The creation of an architecture overview, which includes identifying the architecture to be applied with the secure mechanisms, such as authentication, firewalls. The composition of the application, which identifies the data flows, encryptions, and password constraints for the systems. Identification of the threats, which is used to apply an attacker methodology to identify the possible methods which could be used to threaten the system. The documentation of the threats. So the threats are identified and documented with the type of data or system threatened, forms of attacks, and possible countermeasures. And the ranking of the threats, with the example table shown. These separates it into categories such as the damage potential, success probability, the discoverability, and the affected users, and ranked with the risk of low, medium, or high. The established security tests for UTIP projects. With a growing dependency on modern technology, many systems now require small applications and network solutions. Many of the systems proposed for the VVT class will require certain levels of security architecture. The relanding rocket will require encrypted communications as information is transmitted through the radio frequency. Both the Smart Manufacturing Lab and augmented reality projects will need to ensure proper user permissions and even physical access control. Security tests to utilize include password cracking and file integrity checks. In the event the system is networked, the testing required will be network and vulnerability scans. The autonomous transportation system will also require defined requirements that will identify the level of security. In case the system is hooked to a wireless network, the same network and vulnerability scans will be required along with penetration tests to ensure no harm is to come to a system supporting human transportation.
Hi, my name is Valeria Mendoza, and I'm going to talk about destructive testing. This testing method helps to identify points of failure and also helps to set limits, combining experimental and numerical simulations. Some examples where this type of testing is used most frequently are transportation, aerospace, and defense industries. More specifically, for example, a crash testing in early stages of developing a new model of a car. The purpose of either physical and stimulated destructive test is to reveal systems defects that we can only find when the system is exposed to uncommon and rare events and environments. The data collected will help to prepare different solution scenarios in case of a malfunction that might happen on the field. Now we're going to talk about the advantages and disadvantages. The advantages are that the data collected is reliable because it's something that came from a real scenario rather than assumptions. The results are useful in the design stages since you can modify and directly test if features will work or not and what is the level of risk. We can also advantage of the fact that we can get quantitative limits that will allow to set preventive measures and requirements. Also, service conditions can be measured and the information can be used to set standards. The disadvantages are that the data applies only to the tested systems. It can eventually apply to similar models, but risks exist in not making a new test for each scenario. Test specimens or material can only be used once, which leads to a high expense and waste. Also, to recreate a destructive test will require large and expensive equipment and laboratories. Now, I'm going to talk about the types of destructive tests. First, aggressive environment testing. This contains fracture and fatigue testing in corrosive environments at set limits of temperature and pressures and will allow to analyze the impacts during these conditions. This test can be useful to test the impact on temperature for the relander during the highest and lowest requirements. For corrosion testing, we take non-toxic small-scale corrosion in different environments like fresh and seawater. For fracture and mechanical testing, we can perform tension, bend, drop weight, peel, crush, pressure, and fracture tests. It will allow us to test metals, welded polymers, including plastic pipes. Fatigue testing will be performed in air or seawater environments. These are used to test materials and the endurance of joints under constant or variable amplitude. Hydrogen test will use cover materials that have risk of corrosion from exposure to hydrogen. Can apply a wide variety of temperatures and strain rates. And finally, residual stress measurement. will test the remain in a solid material after the original causes of any stresses have been removed. This can be intentional, such as the scratch-resistant glass on smartphones, or unintentional, which can affect on a structure. This test allows for designers to determine factors like near surface and through thickness residual stress distribution, which can be used in engineering assessments.
Hello everyone, my name is Montserrat Salas and I'll be talking about reactive testing. So what exactly is reactive testing? Its main purpose is to create a dynamic approach to systems testing whereby the individual test cases are affected by the behavior of the system under test. How does reactive testing achieve this? This is done by creating mechanisms in the test facility to observe dynamically the output of the system under test during each test execution step. Now notice that I put a very important note in here, which is that the system under test and the test facility have to run at the same time so that any test actions can be performed using the same timing framework. So you might be wondering when it is alright to implement the reactive testing approach. Reactive testing is usually implemented when the system that will undergo testing is either very complex or is lacking a fixed course, meaning that it is unpredictable and it doesn't have a regular pattern or movement. An example, just a very vague example, could be a mental patient who behaves in a very unpredictable manner. Let's say 1 second he is really happy and kind, the next minute he is super angry and shouting, and then the next minute it's already crying. So this is an example of what erratic means. Basically, the characteristic behavior of systems that undergo reactive testing is that they are not fully predictable, and that is why this approach looks for odd behavior and remote niches of the system. Reactive testing is particularly suited for automated testing, meaning that it depends on the response of the system itself. I'd like to talk about some of the advantages and disadvantages of reactive testing. One of the biggest advantages is automation. Reactive testing is an automatic process, as it has been stated, and therefore it enables the testing of systems with very large amounts of data. It is also reusable because it lends itself to easier reusability during system development stages. It is also very effective, significantly more effective at finding defects than are scripted tests. It is also a lot more robust. It is more dynamic because of the variance over time. Another advantage is that it is very efficient because it does not require as much paperwork as other type of tests, and it is also easier to maintain because individual test runs are generated automatically. Some of the disadvantages are coverage gaps, because it can lead to coverage gaps in the testing space, as the automated testing process may unintentionally ignore problem spots. Moving on, we have repeatability limitation. Let's say that the system under test has memory and its behavior depends on past states, then it is quite difficult to repeat the sequence of test runs leading to the same failure. The last disadvantage is test oracle problems. With pre-designed tests, there is typically a defined expected result or some other way of determining whether the test has passed or failed. In some reactive testing cases, the only test oracle is the judgment of the testing engineer, which it's not very reliable. Lastly, I want to talk about the steps in order to implement a reactive testing. The first step would be to define the system under unit. Be specific about the system's boundaries and its environment. Step 2 would be to define test requirements. This would include the specific elements to be tested and their test oracle. that is, the constraints of their values. Number 3 would be to define the structure and capabilities of the test suite in detail. For step 4, you'd have to define interfaces, and this means the interface details between the test suite and the system under test. Step 5 is very straightforward. You have to define the initial test data. For step 6, we would have to define the test stopping criteria, meaning a test stopping criterion as well as the actual stopping mechanism has to be defined in order to govern the stopping of the reactive testing process. In step 7 is where the actual reactive test takes place, and in step 8 is where you would be analyzing the data that you gathered.